Welcome! Everybody knows that bodies can deform. Deformation, however, can happen under very different conditions and produce very different results. Materials have obviously different strengths, which means that a larger force will be needed to deform a strong body, whereas a smaller one will be enough to deform a softer one. The same material, on the other side, can deform in different manners. The candy bar you see in the picture, for instance, can be broken in two or can be deformed in a continuous manner, changing shape but without losing continuity. In this model of our MOOC, we will focus on when and how rocks break. We will first enter the rock mechanics laboratory, analyzing how rocks deform in a controlled environment, and we will then look at how they deform in nature. The machine you see in the picture is a rock deformation press, similar to the one we have in Delft. The apparatus consists of two pistons which move towards each other, squeezing the rock, and an electric resistance to perform experiments at different temperatures. A confining pressure can be applied around the sample to replicate conditions at different depths in the earth. When the experiment starts, the piston squeezes the sample, shortening it in the vertical direction. Once the experiment is finished, you open the machine, extract the sample, and analyze what the sample looks like. Depending on temperatures, rock can deform in two different ways, defined as the low temperature and the high temperature regime. We first look at the low temperature regime. A common way to display the results of rock mechanic experiments is a stress-strain diagram. On the horizontal axis, you can see the strain, which is the shortening experienced by the sample during the experiment. On the vertical axis, you have delta sigma, which is the difference between the stress applied to the piston and the confining pressure, which was decided at the beginning of the experiment. Note the vertical stress applied is the one needed to keep the formation going at a constant strain rate. In the initial stages of the experiment, you can see a linear relationship between applied stress and strain. This means that deformation can only occur if the stress keeps increasing. If you would stop the experiment here, no further deformation would occur. If you would remove completely the stress, the sample would go back to its original shape and size. We call this the elastic domain. Stress-strain relationships are described by Hooke's law, which states the strain is a linear function of the applied stress. If you continue the experiment, the rock will break. The stress will drop and the experiment will end. Apply a high confining pressure, the experiment continues, and the sample passes the yield point, which forms the boundary of the elastic domain. After the yield point, the stress strain can have different shapes. It can keep on climbing, it can flatten, or it can even descend. The latter case implies that less stress is needed to keep on deforming the sample at the same strain rate. The sample has become softer. You can also see that the experiment continues much further than in the previous slide, and that therefore a lot of deformation can be accommodated. Open the apparatus and cut in the rock, we can see what happens in the various stages of deformation. In the first part of the curve, the sample develops a large number of small fractures spread over the entire rock. With proceeding deformation, old fractures become longer and new fractures will develop. Under low and intermediate confining pressures, fracture concentrate in specific part of the sample, eventually leading to the development of a through-going fault. This marks the end of the experiment. Faults typically come in pairs, the acute angle being 60 degrees and being cut by the direction of maximum compression. At high confining pressure, fracture will be distributed throughout the entire sample. No through-going fault is developed, and the sample will deform, acquiring a barrel shape. Stress-strain curves in the high temperature domain look substantially different. The first diagram shows deformation curves obtained in experiments with different temperatures. Clearly, the rock becomes softer at higher temperatures. On top of this, it can accommodate much more deformation than the colder counterpart. The second plot shows deformation curves with different strain rates. Note that because of the negative exponent, curves in the upper part of the diagram correspond to faster experiments than those in the lower part. The message is clear. The faster you want to deform, the higher the stresses you need to apply. On the other side, if you have a lot of patience and time, you will need very little stresses to achieve large deformation. A third important factor not shown in this diagram is that stress-strain curves for different rocks are very different from each other. From the plots, you can see also that the samples in the high temperature regime can accommodate large deformation, and they do this without losing continuity. Rocks deformed at high temperatures look very different from their lower temperature counterparts. Even when they are highly deformed, they will not break, and the deformations are accommodated by changes in the shape and dimension and structures of the crystals. The sample always preserves the continuity. Rocks that deformed at high temperatures are often called mylonites. Here a summary of the most important things we have learned from the experiments. We can distinguish two different regimes, namely the low temperature regime and the high temperature regime. At low temperatures, samples start deforming in an elastic manner, developing many small fractures spread in the body. At a given moment, there will be so many fractures developing in preferred zones of the rock that they will break and forming a large-scale fracture. This fracture can be parallel to the axis of the compression or oblique to it. At higher temperatures, the behavior is very different, and the amount of stress you need to apply is directly proportional to the rate at which you want the deformation to occur and inversely proportional to the temperature at which you work. Different minerals have different strengths. In general, samples do not break and can absorb as much deformation as made possible by experimental apparatus. Welcome. We've been enough in laboratory. Today, we'll go in the real world looking at how real rocks deform. We will focus on structures developed in the low temperature regime. Remember the stress-strain curve we discussed during the first clip? Looking at deformation structures, we distinguish two stages. In the first stages, deformation is low, typically less than 5 to 10%, and fractures progressively form distributed over the entire rock. Despite the low deformation, this stage is very important because fractures are numerous and have a major impact on rock properties. With increasing loading, the rock will eventually fail, developing a mechanic instability and forming either a fault like the one shown in the picture or a fold. Let us look now at the initial stage of deformation. The most common structure developing are joints. These are planar, very sharp features, often very long and with minimal displacement. Like in the case shown in the slide, joints never come alone. They come in thousands, generally nicely parallel to each other. Joints are often organized in 1, 2, or more rarely, more directional sets. In this case, they form networks, with fracture cross-cutting each other. In the vertical dimension, they can be confined to single sedimentary layers, like in the left picture, or traverse large parts of the sedimentary succession, as it is the case for the rocks on the right. The appearance of thousands of fractures has a major impact on properties of the rock body. It will, for instance, dramatically increase its porosity and permeability, transforming an impermeable rock in a great reservoir for hydrocarbons or water. The fluids massively circulating through the fracture network are often loaded with elements such as calcium or silicium. Under favorable chemical conditions, they can start precipitating, occluding the joints and forming veins. The full closure of previously open fractures means obviously that fracture-related porosity of the rock will dramatically decrease. On the other side, very important ore minerals, such as gold, can also be precipitated in the veins, which are then very beneficial. A very important process taking place during the initial stage of deformation is pressure solution, by which parts of a rock dissolve when subjected to pressure. In the case of massive rocks, typically carbonates, pressure solution leads to the development of rugged surfaces called stylolites, characterized by peaks which are parallel to the direction of compression. Stylolites can be several meters long and often form in bundles. You can imagine how much material is put into the system. In the case of a granular material, such as the sandstone, the larger pressure occurs at the contact point between grains. These will experience dissolution, releasing minerals such as calcite and quartz, which is removed and possibly deposited in the intergranular pores. As we have seen, all these structures only accommodate little deformation. If deformation continues, the rocks will become mechanically unstable and faults or fold will develop. Welcome. In the previous clip, we started looking at how rocks deform in the low temperature regime. We've seen that the first 5 to 10% of length changes are generally accommodated by a large number of structures, joints and/or stylolites distributed over the entire body, absorbing little overall strain. With increasing strain, the rock must adopt different ways to accommodate deformation and will develop mechanical instabilities. These are faults and folds. Today, we focus on faults. Faults are zones of high deformation which accommodate substantial displacement. Faults are features of great importance in geologies. Faults can be active at present and, like in the case shown, even displace riverbeds. These faults are often associated with earthquakes. Faults are also of crucial importance in fluid flow. Most of the hot waters feeding thermal baths move upward along faults. Depending on the relative sense of movement of one block with respect to the other, we can distinguish 3 types of faults. Normal faults, when the upper block slides down with respect to the lower block, causing an increase in horizontal length. Reverse faults of thrusts, when the upper block slides upward with respect to the lower block, causing horizontal shortening. Strike slip, when the 2 blocks move laterally with respect to each other. Strike slip faults are often subvertical and can be sinistral or dextral. Quantifying movements across faults is of great importance. During deformation, the body will become longer, as in the case shown, or shorter. The difference between the initial and the final length is called extension or contraction, respectively. If you normalize this number by the initial length, you obtain a parameter called strain. If information is available on the duration of faulting, one can obtain the rate of deformation. Many geological phenomena depend on how fast deformation occurs. Connecting 2 points which were in contact before deformation, a displacement vector is defined. The displacement vector can be split in a horizontal and a vertical component. Faults are not always planar and can be curved. In the case of normal faults, layers in the upper block become steeper towards the fault and form a rollover anticline. If sediments are deposited during deformation, they will record a progressive change in position. In the reverse fault case, the upper block moves upward and forms also a fold called ramp fold. Because of the curved shape of the faults, the upper block develops particular geometries and structures which are not present in the much more regular and simple planar faults. Faults rarely come alone and form rather fault systems. Normal faults appear often in pairs with opposing dips, form a systematic angle of 60 degrees, defining horsts and grabens. Alternatively, Normal faults can have all the same dip direction and form a so-called bookshelf assemblage. In the third variation, faults develops on the hanging wall of a fault block gliding downwards along a major listric fault. These are called antithetic faults. Association of shortening faults and the related faults are typical for the external zones of mountain belts forming fold and thrust belts. We will see more of this when discussing the formation of mountains. Until now, we have looked at faults as if they were simple geometric features. This is obviously not the case. Along faults, you might find thick packages of broken rocks or layers of shales. The flow and mechanic properties of this fault will be very different. When the sediment affected by the fault movement is only partially lithified, then the grains will tend to slide with respect to each other, forming a deformation band. Grains become a bit compact, and some of them might break, resulting in a decreased porosity of the rock. When the rock is fully lithified and has a massive behavior, things are very different. Some faults can be very sharp, with deformation strictly confined to the fault plane. Other faults can be tens of meters thick and develop fault zones. In fault zones, we define a damage zone characterized by a large number of fractures with little displacement. We define a fault gouge, where rock fragments have variable dimensions and sorting is very poor, and the sharp fault plane. The damage zone typically has high permeability, whereas the fine-grained gouge is often a barrier to fluid. Predicting properties of subsurface faults, even when imaged by seismics, is a great challenge. Here you find a few general points you need to remember on faults. Following the stage of elastic loading, mechanic instabilities will arise and the body might break, forming a fault. Faults are zones of high deformation, separating blocks of undeformed material. Faults accommodate large deformations. Faults have variable structures, resulting in variable physical properties. Welcome. We've seen in the previous slides the rocks with increasing deformation develop first fracture system distributed over a large portion of the body and eventually become mechanically unstable, forming faults or folds. Today, we will focus on folds. Folds are characterized by the homogeneous distribution of deformation over the entire structure. Differently from faulting, this means that a rock body does not lose its continuity. Folds can occur at all scales and often form impressive features in the landscape as well as in the subsurface. Folds in the subsurface are very important for applied purposes, as they can form traps of hydrocarbon, forming seals, or, especially when fractured, reservoirs. In the slide, you can see the most important geometric parameters used to characterize folds. A fold is composed of two flanks or limbs, which are connected by a hinge zone. Depending on the angle between the flanks, the fold can be more or less open. The line parallel to the hinge zone is called the fold axis. The plane, which contains the hinge zones of the folded layers, is called the axial plane. The surface connecting the hinge zones is the enveloping surface. When this is perpendicular to the axial planes, the folds are called symmetric. This is the case of the fold shown in the slide. Additionally, geometric elements are the wavelength and the amplitude of folds. When layers are shortened, they can develop folds which are convex upward or downward. In the first case, they are called anticlines and have the oldest rock in the core. In the second case, they are called synclines, and in the core you will find the younger rocks. From a mechanic point of view, we distinguish two different types of folds: buckle folds and fold band folds. If you understand the mechanics of the specific fold you are interested in, it is much easier to predict its structure, properties, and evolution. Buckle folds are generated by horizontal shortening affecting a layer or bundle of layers surrounded by softer lithologies. From the equation, you see that the thicker the folded layer is, the larger the wavelength will be. Similarly, The wavelength of the fault also increases when the viscosity contrast increases. A very different type of fault develops when the layers experiencing compression break along a reverse fault. Typically, these faults run parallel to bedding for a certain distance and then cut across the stratigraphy, eventually reaching another level of flat position. Because of this staircase shape, the hanging wall moving up along the fault will have to adapt to the non-flat geometry of the fault, thereby creating a large anticline flanked by two smaller synclines. In the summary of the animation, you can distinguish two different stages occurring with increasing shortening. Initially, the anticline becomes higher and higher. When the hanging wall ramp has passed the photo ramp, then the anticline grows only in width and not anymore in height. As you can see from the slides, the geometry of the passive faults is controlled by the geometry of the thrust surface. Indeed, something very different from what we've seen for buckle faults. Similar to what we've seen for faults, faults rarely come alone. Trains of buckle faults are found in areas where the rigid group of layers is underlain by easily deformable rocks such as evaporites. This is the case, for instance, in the Zagros Mountains of Iran, the Salt Range in Pakistan, and the Jura Mountains in Switzerland and France. In map view, you can see the succession of anticlines and synclines nicely following each other. Systems predominantly composed of passive faults, fault band faults, are very common in the external zones of orogenic belts. Here, convergence between the plates is accommodated by thrust surfaces with the typical staircase geometry and associated fault band faults, like the one shown in the rectangle.